Hi chemistry kids, so we're doing our final little dot point, and I'm going to try and divide this video up into those 3 parts that you see on the bottom. So we're looking at calorimetry. So I did the video before where we were looking at just burning the food. That's the very basics. We're going to go into a bit more. Going to look at solution and bomb calorimetry. Details on these is weird. Like I look and they mostly give you the information about them, but you probably will have to compare or know how to compare. You've got to be able to determine a calibration factor and consideration of the effects of heat loss, i.e. when we don't have a perfect system, because we never have a perfect system. If it looks like it's a perfect system, then something is dodgy. And then you're going to look at temperature time graphs obtained from solution calorimetry, so just the solution calorimetry, to give us these graphs. This is a good thing to think about in terms of your GAT, because you have to think about graphs and what they mean. So that's our last dot point. It's kind of 3 bits: is solution and bomb calorimetry, calibration and calculations around working out our energy and food, and then some time graphs. So I think there's a lot, but it's pretty doable in the time. So we've got our 2 types of calorimetry. I always want to say calorimetry, because we're finding out our calories. So remember, I was burning my food, changing water temperature. That's the basics of this, just more complicated. So we have bomb calorimetry, which gives us this sealed vessel. So we have a sealed bomb here, and what we do is we put our food sample in the vessel. So we've got a sample of cracker or whatever it is, and we attach that to some wires, and then around our actual bomb we have water and a stirrer and a thermometer, and then some thick insulation. So what we do, we put our cracker or whatever in here. We've got a known volume of water in here, known volume, and we stir it around, and then we use the ignition here, like the clicky thing I used to burn my food. Click, 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 poof. This starts combusting in the oxygen. It's going to burn just like I did. It's going to give off heat out to the water. This is going to move the water around, and we're going to see a temperature change, either an increase, well, mostly going to be an increase. So the whole vessel is nice and insulated. This is all sealed as well. That's sealed here. Just got these coming through here. So it's a really nice closed system. So generally we're not going to have much heat loss from this, but it would be expensive, and schools generally don't have these because they are expensive. What we do have is we have solution calorimetry. So we could use just a simple polystyrene cup for this, and it's about the reactions that occur in a solution, hence the name. They're not trying to be tricksy for once with a weird name. We can't use this for food because we're not doing combustion. This is just mixing 2 chemicals together or more, but it would only be 2 at this stage, and seeing what happens to the energy change. So it's putting something in, generally water, your stage is going to be water, and then seeing how much the energy changes. So again, we have a heating coil. We have the reaction mixture that has a known volume of water again, because we want to see that energy change, and if we don't know how much water we've got, it doesn't really mean anything. We've got insulation around the outside, nice and thick. We've got a lid. We've got a thermometer here so we can see the temperature change, and we've got a stirrer. So I got one from work, but I wasn't clever enough to think about bringing in any wires so I could actually make it do. So it's just that. Sits in like that. We've got this wire that we can put electrical things to. We've got this that we can use as a stirrer, and even you could, I suppose, if you put a lump of something on here, you could drop it in. Pop it in there. Pop a thermometer. That's our stirrer like that. Pop a thermometer. Where's my thermometer gone? Here. Use a pencil for a thermometer. That. And then we've got a lid. The weird thing is I can't figure out how to make the lid work. I think somehow you've got to take these bits off, but I can't figure it out. And I don't want to mess with it. So you can put a little solution in there, measure the temperature change, and see how that goes. So that's our solution calorimetry. And this is the one you're much more likely to see just in a normal kind of school lab. We can have a bulb down here or something. So you can have whatever your solution is down here, and you could kind of break it. So you could use that to break it. You could take the lid off, put something in, close it. Wouldn't be hugely accurate, and think of all the heat that would be lost by just taking off the lid. That wouldn't be great. And then we're going to look. We're going to look at the reactions that happen. So if we've got a delta H that's negative, this is way back at the beginning. We've got an exothermic reaction. So we've got an increase in the temperature of this water around here. If it's a positive value, then it's going to be endothermic. It's taking in the energy, so we get a decrease in the temperature. My quick look didn't give me any of these ones, but it doesn't mean they're not going to give them to you. So, yeah, don't get too complacent if you're seeing a pattern and you haven't seen something. That doesn't mean this isn't the year they're not going to throw something else at us. So we're using this. I'm using one, you're using one. This one's got all kinds of cracks and holes in it. Someone's poked it with pens or whatever. We're not going to get very good results. So what we need to do is calibrate our equipment. So all of our calorimeters have different properties. This one, you know, is this size. We might have a bigger one. There might be one from the same company where this metal is slightly thicker or thinner. You know, it's obviously been used. That might affect how well it works. So we need to calibrate it beforehand. So calibration is really important. You know, if we were going to test some drugs or do whatever, I want to know that equipment's working perfectly well and is all brilliant. So calibration is, so yeah, that's what I basically said. Because all calorimeters are going to have different property, we need to do some calibration, and we use this for all experience. So they talk about in the book doing the experiment, then doing the calibration at the end, which I see is a thing you could do. I would suggest you do the calibration at the beginning, just because it gives you a handle on the equipment. Neither is wrong. I just like the idea of maybe doing it a couple of times to figure out that calibration and then going back to it. So that's just my little hint. Right, so we've got this formula in our data book because we have. So first we're working out our energy. So that isn't in here, but what they've done is they've combined all of our equations into one. So they've combined all of our equations into one. I'm going to break them up into two for degrees of making it easier to work out and go step by step. I would suggest you eventually do it all in one, but kind of doesn't matter as long as you know what this is. So we've got this one that we're going to use. This one we've already used. This might come in to what we're doing as well. So we've got this big equation. I'm going to break it up into two. So we are going to have our energy equals VIT. So this is our calibration, and we run it to work out how much energy we need to make this solution in here. So this solution in here rise by 1 degree. That means that then we have a known value for this piece of equipment, and we can compare whatever we get with that known value. So the way we do it is we would plug this in here and here, here and here, if I show here and here, into an electrical box. What are they called? You know, the electrical boxes we use. And we give it a known voltage, a known ampage, and we do it for a certain amount of time. And then using that, we can work out how much energy we have put in. And then that can be used to work out how much the water has changed temperature. So we've got E, which is our energy released in joules, which is what we're trying to find in this first steps. I've seen all kinds of examples. So the Jacaranda, off the top of my head, says always do it in joules, but I have seen both. So I would say stick with joules, but if the number starts to get big, either use scientific notation or use kilojoules, but make sure you make it clear that you understand joules. Then V is our potential difference in volts. Potential difference in volts. I is our current in amps, and T is time in seconds. So this is what we'll get given, and then we have to use that to, we'll get given these and we'll have to work out the energy released. So that's where we're going with that. I'll go through an example because just showing you this kind of doesn't mean anything. Right, so we've got from this, we've put these numbers in here and we've got our energy released, and then we can work out a calibration factor. So that's specific for that piece of equipment. So our calibration factor is energy. The calibration factor is which is the same as that VIT. I've just again broken into two steps. Is my energy released divided by the change in temperature. I've included this C, not all of the books do, but I've included this C to say this is calibration. Then that makes it clear to me when I do my next one, when I'm looking at non-calibration, what I'm looking at. So if I've got a big question and it's got lots and lots of different parts in, if I know this is my calibration change in temperature, and then I've got later my reaction change in temperature, I'm not going to get those two mixed up. I can label above my question. So I've worked out my calibration factor. That's great. Now I've run my experiment where I've put something in. I should have an example. Or I've put something in here, in some water. I've got an energy change. I've measured the energy change. What I can do is I can measure that energy change. I times it by my calor. So this is my reaction. Energy change. And then this is my calibration factor. So that's how much energy I need to get a specific 1 degree change. So that's very specific equipment to equipment. And then my work to get my delta H, I have this energy change here, and I divide it by my number of moles that I've put in. And that gives me my delta H for whatever I am using. So the example I've got is a bit long-winded. No, a bit long-winded, but we'll go through it together. And it's a good example of, oh God, this question. Right, so an experiment was performed by a student to determine whether ethanol is a suitable fuel. The student burnt 1.5 grams of ethanol in a bomb calorimeter. The calorimeter was calibrated by passing 15 amps current. PT. Oh, potential difference. The potential difference of 5.5 volts for 2.5 minutes. The temperature rose by 1.7 degrees. Part A is find the calibration factor. So is find my calibration factor. I'm going to do it in pencil because I always mess up this stuff. And then it makes me feel better. And where's my calculator? So, got my calculator. Again, no shame in using the calculator. So, first I need to work out. This fits my E. So, I need my E. So, I want to find E. What I have is I use V, I, and T. And I keep using this. You can never see very clearly with pen. This pen. VIT. Right, E equals VIT. I'm going to break it into those two steps for you. So V is here. V. My I is here. I and T is here. But I need to convert into seconds. So my E equals V 5.5 times 1.5 times 2.5 times 60. So that's to give me my seconds. I've like 3 different calculators and all the buttons are so different. Because I've only got 3 significant figures. 2 significant figures. Oh, well, don't simplify to the end. Keep going. I don't know why I simplified. So that's my energy, but I want to know my calibration factor. So the next step is my calibration factor is equal to E over delta T. See, for my calibration, like the time in my calibration. That is equal to 123.7.5, or answer in your calculator. Make sure you know maybe how to store a few answers in case you have to go back and use it again. I don't know how to do stuff like that because I'm not that smart. Or make sure you're writing things down because you can always circle things when you get to the end. 1.23345 divided by my temperature change, which they've given you don't have to work out, divided by 1.7. Divided by 1.7 equals 7.3 times 10 to the... I shouldn't have to count, but I do. I ain't no shame at it. So that's working out my calibration factor. If the water increased in temperature 10 degrees, find the delta H of the ethanol. So there's going to be a couple of steps to this. First using my calibration factor and then using the amount of moles that I have of ethanol. Right, so I've got my calibration factor that I need to move across. Doesn't help when you have to go on other pages. Oh, also remember, if you have to use another page, you have to tell the examiner and they have to note something down. So if you have to go on another, just try not to go on another page. My calibration was 7.3 times 10. Right. So I need to work out the delta H. Delta H. Ethanol equals unknown. And what else do I need? Oh, I need the delta T of the reaction, which was 10. So I've got these numbers and what I have to do is use them. So I have these two. I'm using these two to find this one. So first I need to know I want to find my energy change. So E equals 7.3 times 10 to the 2 times 10. Just gives me 7.3. And they've given you a very easy number there. Then I want to know how many moles I've got. So and hopefully I write this down. So how many grams did I have? I had 1.5 grams. 1.5 grams. Make sure you do that decimal point. And my 12 times 2 plus 16 plus 6 equals 46. Which gives me oh, helps if I can use a calculator. 0.326. So that's how many moles I put in, or he put in, they put in. And so per mole I have right. So I just then noticed that I can't copy from my calculator. So here's my answer. So 0.033. Make sure you're including that 0, because otherwise you're going to be a factor of 10 off, and that's not great. So we've got that many moles, we've got that many joules. What we have to do is now divide them by each other. Divide them by each other. It really helps if I can English, which I can't today. So we take this amount of energy, 7.3 divided by 0.033, delta H equals, which gives me the way around. No, I haven't done it the way around. Just in big. Right, so that's my delta H. Just check I haven't missed anything out or done anything weird. No, that seems okay. Make sure I've got my unit. So 2.2 times 10 to the 2 joules per mole. Right, next question is compared to the data book. My heat of combustion is somewhere below. The ethanol heat of combustion is like way off, absolutely way off, which makes sense because he would have been doing it under less than ideal conditions. But in heat loss, there would have been all sorts of stuff going on. So, I mean, it's not hugely awful, but it's not great either. Yeah, it's not great. So that's how we work those ones out. There is some worked examples I put in that folder for you and you can look at them on Jack Plus where they're going through a slightly different way of doing it, and they have done the maths beforehand, so they're not doing silly things like missing out decimal points. Then we can do chemical calibration. There's a lot. Chemical calibration is, well, when we can burn, so when we're in a known amount of